Kole ngambulo luku. With whatever we do. Jioni safu nola. With whatever we do. Hale yide munyu skula. Nyepamne ne kudlukula. Nyepangi ragala gena. Nyepamne ne kudlukula. Ibuloke numoto ni beti sola. Ibuloke dato ni betoto.
Mingi Congo.
Lamin.
Na?
Lamin te jibe norin te nyame Lamin.
Kabana wulo kono.
Wulo kono nyinte mo Lamin.
Pabilenki.
Muna ngata afongole.
Haina.
Ngata. Ngoto le. Fabrama.
Mingi. Baba nyola.
Ngoto le Fabrama.
Namu jumala kan kuma diten.
Fabrama.
Jumala mu.
Ndele bare muso.
Lunda mana.
Kata.
Jamani mbere.
Alindo ko.
Jamani.
Bari ngoto man kontande.
Bari jamani fana na mudu ma kontan.
Ngoto minaka ngalamin de fom filitala. Lamin jibe nori nyala.
Lamin ila siran sama ne benki. Yala so tol sayni no ko mo lakko momo.
Ngoto.
Nam.
Itedinte yalo ne Lamin hakilo diata bake karambu ngoto. Anu santeng ministry ko di ngole si suwo ko amake ko do holi de
si bitun
bagona de
ala ni ko kede namo balo
ala ni na ko ina karta bulo be damna ala ni je
ngoto
nam
ngoto mon kontan fere
jamani mu nekata
ite ka Lamin ki wulo ko no nyintay mon ko do fete malo Lamin nyanta sila la be la moy kala karango
jamani karamol be sorande ne ko fasita wulo ko nako
karambugol ma soron ni ko karambugol soron da amake kom holiday lem ngoto dini ngo nyanta sila la ala karango la moy yamen kamen fue man kontaan andamande
alla nyin kombo courant adanda la kombo len do la jankara mol le soron do kamen courant ma do la kombo e to ndol fana na kara mol soron je kara mol soron Lamin adara lo nyino la amantara fe na sokon ala munekela
am Lamin ite foyde malon ko lesinol be ke kar radio to
nga fine
e ko yana di mod Lamin ya muna fonye
bi kabin mina kan ntambita nteri maning Fatou ntambite la sukol ala dinngol bebe siri be la moy ka
Fatou danso am fana tambira jele ni subala la ngaje diningol be jet talanta nen kili warol e be serin jelet
sa Lamin fadante ku kili wo ke no la ba Lamin bita ka wulo ko no nyin taymo Lamin
amandara fennela
ite dine ko ni man si yakari lesino la moy radio to balon nan
muneka ke afonye ba nyara ni alon
telentel jikot
afonye ba munebe ke
ite balon tel be jikritel ni man karambe ku kele yaje nata karana mbasa malaya ay tarije
par ñarande kombo courant ho findira kombo ide nara yede ni sonka bay ko Lamin ma ñata la wulo ko aru kara mo be so da fa ñembe be
ko to wole nati ba ngal le ni Lamin kuntal kombo courant o ka fa me kombo courant asototal wala kinay ko e si suwo kono bari ni ko e si suwo kono ibe karangol dike la radio ni telel to hani tele masoto to nyaay man tele soto la bungo bar radio be bulan koto batiri sanga ay si ay alamo
sa do kala nyaadi
ko ta o bulaji
abe kala nyaadi
kamun ke nyaadi
radio abe wala moy la ibe mona falaje
ibe la karandirol kala jele
ti talle be radio ko men ga karande
ila subject ro baby jele baby jele
wala nanga coco moy fa dan so wolya ngombe tambi kana ngadi ningol de be ikadum bungo de ko kada ma mo
asototal de
Lamin mala be kara wala de
bari laftalal ideal on ko inde every year second wala fourth
muna ni ko nde ko folle sinila mba ndele sinilo ne ba
say mba foke en koto wole fango yen wulindi yalo famo keta bat ñu fana bulata ko ko me yen nati jambi Lamin nyanta karana ndel be jiko be nyineka ya bulay kara wulo kono ta kilar ya bambalo yo be bulaje koto dindi ngoy si ayala le sino la moy radio
wara ga munda kara mo man soro Lamin nyanta kara si suuna regular
silale ayala le sino
dal ko korna ko smolon
kilar ya
mo be ngala ko momo say mi do ni kono kera
mengi bruzo
ndebe ko do la da ba rosa no radio ba no bari woro radio ni abe jele ba ngamra do man dembe buljan dala nyara nyar fo ko fendi mo la Lamin tayra ba rosa
bara te ku folo ajibe nori nya Lamin tamete ku
teku
bari ko do famo ke
image nani nyambol sizol le keje kisigi man sizol ndol le kafun ka nyoma bari nyambu kino ni manya na kafindi ni nambe ko rozor la ga
ngale limbeta de be nyambo do dilanna
nyara ni ko rim fennat nyara nata
bari famo ke da
ngata bungono Tami bungono nyara ngando ko fele ko ke baru nganda ni pelo la ndija
iyo awe betar la
bungono bismillah bisu diara
Pendulala ye fongo tanka sina dolu tanka koro ta koro ta
Hello viewers and listeners. My name is Samuel D. Kwede, and I'm here to continue our lecture on waves. Remember, we started off with the definition of waves, and we went through the types of wave, the properties of wave, the mathematical representation of wave, and along that same slide we said we are going to talk about sound waves. So this lesson is about sound waves and about resonance, about vibration in strings, and that ends our lessons. So we kick off from there. And on the board we have sound wave. What is this sound wave? We say sound wave is a form of energy produced by a vibrating body which propagates through a continuous medium, and on entering into our ear produces the sensation of hearing. You know, like you're hearing me now, it's because there is air here. If there is no air, there is no sound. Remember that? That is one condition for sound to be affected. You must have a medium. That medium is going to be air in this case. So sound is transmitted, the sound energy passes through that medium and it goes to your ear and it gives you the sensation of hearing. That is what sound produces. So remember, sound itself is a form of energy. Like I said, it's a form of energy produced by vibrating bodies, and they propagate through a medium, a continuous medium, and on entering into our ears produces sensation of hearing. All right, so now we have already got a definition of sound wave. Now we look at the classes of sound. You know, some of you produce a lot of sound, and sound can be categorized into these classes. First is musical sound. You know, some of you like music a lot. So musical sound is a class of sound that is pleasant. That's why you enjoy it. You say, I like this music because it is pleasant. It's a pleasant, continuous and uniform sound produced by regular and periodic vibrations. You remember the terminologies there. I just told you that it is first musical sound. I've just given you the properties it contains. I said it is periodic, somehow, that it is timely, it is a uniform vibration, so it's regular vibration, it's regular. And that is the more reason why you'll be able to dance to the music, because if it is not periodic, you will not be able to dance to the music, you'll not be able to organize your steps according to the sound produced. So it must vibrate periodically, it must be a regular vibration frequencies assembled together. That is what gives you the musical sound, and they say, I like this music. Example is a sound produced by pianos. Some of you have seen the piano, and you have seen flutes, and when the sound they produce are all organized regularly. So that's why you enjoy the musical sound. Look at another second type, which is noise. Noise is a class of sound. The next class is an unpleasant class, which is a discontinuous and non-uniform sound produced by irregular and non-periodic vibrations. Now, it's just like a reverse of this, or the opposite of this. It is non-periodic, that it is not categorized according to the properties of sound wave. Very soon you see the properties there. And two, it is not regular, so it's not regular. So what are we saying here? Since it is not uniform, it's not regular, it is actually a random mixture of frequencies. That is the more reason why we say keep quiet, there's a lot of noise here, because this guy is speaking, the other guy is speaking, producing different sounds with different frequencies. And when those frequencies interact, they produce a non-regular and non-periodic form of vibration. And when that happens, that sound is unpleasant to you. So we call it a discontinuous and non-uniform sound, which is referred to as noise. Example is a type of sound produced in the market. When you get to the market, you see this guy is selling, you have somebody selling this article, he's shouting, he's pronouncing something, somebody's singing over there, and you see different sounds with different frequencies, they interact together. Now, sound produced by horns of vehicles also, it could be a noise there, and bombardment or blast, bomb blast that is also executed by bomb explosion also gives us a time of noise. So you can now distinguish between the sound produced by music and sound produced by noise. So these two classes of sound wave will help you to go to the next. First, before we get it, we want to look at the range of frequencies in which you expect sound to be heard. You know, sound is, we said, is a continuous, it's a regular vibration of materials, or when elements vibrate, they produce frequencies, and those frequencies are heard by our ear and we get it. But it's not all the frequencies you can actually hear. So there are frequencies, there are range of sound. So I call it range of sound wave, or ranges of sound wave. First range is the audible range, that is the audio range. The audio range or audio spectrum. Audio range or audio spectrum. What do I mean by that? I said the sound is a continuous production of frequencies. Now those sound waves you produce have frequencies. And if the frequency of that sound wave is between 20 hertz and 20,000 hertz, then you perceive the sound as what you are getting now. If it's because the sound I'm producing as regular vibration, regular conversation actually is having a frequency of around 1,000 hertz. So you can see 1,000 hertz, that is regular vibration or normal conversation. This 1,000 hertz is falling between 20 and 20,000. So I'm expecting you to hear, because the sound I'm producing now is audible. That's why we call it audio range or audible sound. That sound you can hear. And that sound that has frequency between 20 to 20,000 hertz is what is called the audible sound. That's what you can hear. And that is the range in which we can hear. That's why I say be audible. So now we have the second type. The second type is the first, is the ultrasonic. Ultrasonic sound. What's that ultra? Ultra means above. Ultra, we said above. So above this audio range, there's a set of frequencies also which we also produce on sound. So sound above the audio range is what is called audio frequencies, or call it ultrasonic sound. That sound wave is above 20,000. So when sound is above 20,000 hertz, now that sound wave is referred to as ultrasonic sound. That sound wave is not supposed to be heard by you. It will damage something in your ear. So that is the more reason why you have to be careful when you listen to sounds that are above this frequency. It is, in fact, sounds along these frequencies are really heard by human beings, because that's not your range of hearing. So we have the third type. The third type is infrasonic. Infrasonic sound. Infra means before the sound we can hear. That is before the audible range. So before the audible range, that is below 20 hertz. When the sound wave is below 20 hertz, that sound is called infrasonic sound. Infrasonic sound is a compression wave frequencies that are under the audio range. Under is infra is below. So below the audio range, you have this infrasonic sound, and above the audio range you have the ultrasonic sound. So you must be able to understand the two there. First, I said the range of frequencies of sound wave that is audible to the ear is what we perceive as audio range, and the range of frequencies that are above that audio range is what is called the ultrasonic sound. Those ultrasonic sounds are above 20,000 hertz. So this one is the infrasonic sound. Infrasonic sound are whispers fall there, or subtle voice comments all fall into that category. That is, you don't want to beat, you don't want to produce a large frequency to be able to transfer the energy to the point. So whispers most times will fall there. That's why somebody say, I can hear you, be audible. So that means telling you that move from infrasonic range and get into the audio range so I can get you. So now you now know the ranges of sound wave. Infrasonic, I've just said that this is the compression wave frequencies that are below the audio range, they're below 20 hertz. So how do we produce sound? We produce sound wave by vibrating element, of course. We'll see, some of you have seen a guitar. Or what is happening to me now, my vocal cord is vibrating and producing the sound energy, and the sound energy is sent into the air molecules around me, and they produce that energy, and they receive the energy and take it to your hair over there, and you get it from me. So you now have one type of vibrating element called a string. Guitar is when you pluck the guitar strings, it is going to vibrate. If the frequency of vibration of that string is within this range where you can hear, then you can actually hear the sound. But if it is not it's not between your hearing range, you will not hear. So when I pluck a guitar or I just press it down, you have what is called a sound produced, and that sound is from that string called the guitar. So membranes also is another material that will produce an element that produce sound wave. Drums fall into that category. When you hit the drum, or maybe the drum was made from some animal skin, that's a membrane, and when it vibrates by hitting, you have what is called sound produced. If that vibration has a frequency that is within the audio range, then you are bound to hear that sound. Air columns also, pipes and organ flutes are in that category. Air columns, when I pump in air into a particular column, and that air vibrates in that column to a frequency that is capable of hearing, that is, it is between 20 to 20,000 hertz, then I will be able to perceive that sound as a sound wave. So air columns also produce sound. And we have other elements that also produces sound, like the bell in your school. When you ring the bell, the gong of the bell or the hammer will hit the wall. When it hits the wall, there is going to be a vibration. That vibration produces a frequency. If the frequency is audible enough, then you can hear the sound of the bell. That's when it's break time, they ring the bell. That type of instrument is what is called the percussion instrument. What type of instrument is a percussion instrument? It's that instrument in which the sound is produced by hitting objects against each other. So you can have the drum and the drumstick. The stick and the drum are two objects. When you hit the stick onto the drum, they vibrate and they produce that sound wave for as much as it's within your hearing range that you get it. So percussion instrument can be instruments that produce sound wave when you hit two objects together. You can also do that. That is, you're hitting two objects together, your palms together, and you produce sound, just like you do in the drum and also in the bell. The talking drum, you already know the talking drum. That's a small drum and the gentleman used to put here, and he would just be hitting it. The stick there is hitting is one object, the drum is another object, so the two of them hit each other, and there's vibration. The xylophone, some of you have seen the xylophone, is something like has a lot of sticks that are joined together, and those sticks are all arranged according to frequencies. Remember that. So the xylophone, you have another stick that you hit the xylophone. So the xylophone is one object, and the stick you are hitting it is another object. So the two of them hit together and they produce the sound wave. That is called percussion instrument. So I've already given you the categories or the production of sound wave by element. Now we can also classify sound wave. You know, classification of sound wave, like I said before, we can also look at some of the characters or the characteristic of the sound wave. Yeah, up to now, the sound can travel through any kind of matter, of course, but not through a vacuum. Remember, we say it's a mechanical wave, and a mechanical wave requires a material medium for its propagation. If the medium is not available, then we can't. So sound wave requires a material medium, and that material medium must be a matter medium, let's say, and you have air in this case as that medium. So we say sound travels through any kind of matter, but not through a vacuum, because vacuum is empty, there's no matter in there. You need a matter medium for that propagation. Number two, the speed of sound is different for different materials in general. Of course, if you look at the three basic classes of matter we interact with much more, that's solid, liquid, and gas. So that is the more reason why sound travels faster in solids, because the material compactability will help the sound wave, the energy of the sound, to travel from one point to another, because the material is already available. And you can see it goes down as I go towards liquids. Liquids, the molecules are not tight, like not as firm as the solid. So you see that the separation, the molecular separation is different in that case. So as the molecular separation differs, that is how the transmission of the energy from one molecule to another also differs. So sound travels faster in solid as compared to liquids, and it travels faster in liquids as compared to gases. So now the molecules are separated apart and they are moving in random motion. So now the general concept is that when the material have particles that are compacted together, the sound energy travels through those material very fast as compared to when they are not close together as compared to the liquid and the gas. So sound travel much more in solid, faster in solid, and faster in liquid than gases, meaning that it can run very fast in solids and can also run, if you compare liquid and gases, it can also run faster in liquid and gases. So, and the third one we're going to look at is the speed of that sound in that gas, to be specific. So the speed of sound is going to change as the temperature of this gas is changing. Remember, I said it actually travels slower in gases, but if I compare the temperature of that gas, then the speed also has a relationship with the temperature of that gas. So it's if I increase the temperature of the gas, the speed of sound in that gas also increases. So it depends upon the temperature. The speed of sound in a gas is dependent upon the temperature of the gas. Now I have already classified the materials in which the sound energy can transmit, and I've told you that it travels fastest in solid and faster in liquid and fast, let's say, in gases. So let's see what happens to the speed of sound in different media, in different materials at room temperature, let's say 20 degrees Celsius, and at a pressure of 1 atmosphere. So see this table, you have the material. For air, it is at that temperature, air is approximately 343 meters per second. And for air at 0 degrees, you see, you have 331 meters per second. And in helium is 1005, as you can see. Hydrogen is 1300, water is 1400, and seawater is 1560, that is 1560 meters per second. And in iron and steel, remember how dense and thick is that? It's 5,000 meters per second. You can imagine that. And glass, if you see, glass is 4,500 meters per second. And in aluminium is 5,100 meters per second. And you have in hardwood is 4,000. And in concrete is 3,000. So you can see the density also plays a role in the speed of sound in medium based upon a specific temperature. Let's consider it at 25 or 20 degrees room temperature. So look at that stuff over there. So let's try and see what we have said so far. I've just given you the definition for sound wave. I gave you the classes of sound wave, and I gave you the range of sound wave, and I'll be able to give you the type of the speed of sound in different media. So now let's take one question here. You see the question reads, it says sound wave travels with the greatest velocity in which type of this matter? A, it says gases, B, liquids, C, solids. Yes, Babakar, what should be the answer? Babakar, you're correct, it says solid here. That is the solid. It is the material where the sound wave travels with the greatest speed. So that is solid, the C in that case. Now let's look at number 2. Number 2K says, which of the following frequencies can be perceived by human beings? Remember, I just gave you the audio range as between 20 and 20,000 hertz, and I gave you the ultrasonic sound wave, which I said it is not to your hearing, it's above your hearing range, that is 20,000 range, 20,000 and above, and you have infrasonic, which is below your audio range, which is less than 20. So you can see the options over there. I'll read the questions for you one more time. Which of the following frequencies can be perceived by humans? Remember, I just gave you the ranges here, which can be perceived by human. Now, A, it's 10 hertz. B is 1,000 hertz. C is 100,000 hertz. Remember, I said 20 to 20,000 hertz is the range of frequencies that are audible to the ear of the human being. So 1,000 hertz is falling within that. So I wanted Fatmata to answer that question, but I just beat the guns. But don't worry, that is the correct answer. The answer is B. B is 1,000. 1,000 is between 20 to 20,000 hertz. And you are hearing me now because at normal conversation, the frequency of normal conversation, sound produced by normal conversation, that is what we are doing, it's around 1,000 hertz. So that is what is making you to hear, because it's falling inside your audio range. So because it is inside the audible range and audible spectrum, you can hear that. That is B for that question. B, 1,000 hertz is the audible, it falls inside the audible range, so we can hear that. Now we go to the properties of sound wave. Remember, all what I've said so far is just a description of sound. Now I want to look at the properties of sound wave. Sound has these properties. Watch out for this. First, I said you may have the property and its effects on the human being. I'm going to focus on the human being much more. So you have the property, number one, property, and you have the effects on the human being. So the property one is the intensity of the sound wave. What is the intensity? The property is intensity. Intensity is actually the rate at which the power is transferred per unit area. So it's given by the power over the area of which that energy is going to cover. So that's power of the sound wave to the area in which the sound wave is going to cover. That proportion, that ratio gives us the intensity of the sound wave. And you know that this one is measured in watts and this is meter square. So we have watts per meter square. Now this tells you that the farther you go away from a sound source, the less the intensity. And the closer you go to that, so there is a business between, actually if sound is going through, I can say it is inversely proportional to the area. And if sound is radiated in a spherical field, because sound is radiated in the sphere from a source, so the area of that sphere is, let's say that it's a sphere, so 4 pi r square. So all of this is constant, so we can see the radius, that is the distance or the area covered by the sound, is having a relationship with the intensity. So the intensity is inversely proportional to the radius square, which the sphere in which that sound wave is radiated. The sound wave is actually radiated in the sphere, and the radius of that sphere has a link with the intensity. So it tells you, even when my area is inversely proportional, so I just decided to fix it inside, assuming that the sound is going to cover a sphere, an area that is equivalent to the area of a sphere. So I put the area of a sphere from here there, and I was able to know this link. So watch out for this link when we get to the questions. So that is the intensity. The intensity, the effect on it on the human being is the loudness. So we have the loudness. Now that is why if a siren of an ambulance is approaching you, the pitch, the loudness of that particular sound is going to be higher, because as the ambulance is approaching you stable, it's coming closer. When it is coming closer, what is happening here is that the area is becoming smaller. When the area is becoming smaller, the intensity is increased. And when the intensity is increased, the effect on you, the listener or the observer, is the loudness of that sound changes. It becomes very amplified, meaning the loudness increases. That is the more reason why you hear the sound as it is coming closer to you, you hear it louder. But when it is going farther away, when you are stable and the ambulance is passing, the siren of the ambulance is moving away from you. When it is moving away from you, you are stable. The source is moving away from you. The area is increasing because the distance between you and the source is becoming larger. So when it is increased, then the intensity, when the area increases, the intensity becomes smaller. Now when the intensity becomes smaller, the effect on you, the observer or the listener, is the loudness of that siren is going to be small, it's going to be very low. So that's the more reason where you will hear why it is passing through. It is damping. The sound is damping. The intensity, the loudness of the siren is damping because the siren, the ambulance is moving away from you. And if it is moving away from you, the area is increasing. As the area increases, the intensity is also reducing because it's inverse proportionality. And now the loudness is the effect on you is going to be as a low sound as it is moving away from you. When it's coming closer to you, it is going to be louder. So that's first property. The second property is the frequency. What is the frequency? We said the sound wave vibrates in loops, and the number of loops tells you the frequency. The more, that is actually telling you the number of vibrations, the number of circles I make per unit time. Remember, the sound wave, as we treated it, it's a series of vibration wave frequencies that are audible to the human ear. Now, the frequency of that sound wave is interpreted as the pitch on the human being. What is the pitch of that? That's actually the shrillness of the sound in your ear. So it is directly proportional to the frequency. If the frequency is increasing, then the pitch is also going to increase. Remember their relationship. Now, the effect of frequency of the sound wave on the listener is the pitch of that sound. The pitch of that sound also increases as the frequency increases. Now, we also spoke of the harmonic content. What is the harmonic content? Now, for vibration of sound, we have the first, let's say, we have sound wave that is having a lower frequency. That lower frequency is actually having, let's say, one loop. That's the first frequency. We call it fundamental node. And now, that is a sound wave of lower frequency, because the pitch is going to be lower, as a matter of fact, because the frequency, which is the number of circles made, here is only one circle. So now, within that same length, if I produce a sound wave that makes two circles, and that takes twice of this, now you can see that within that same length, I have produced a sound wave that has twice the frequency of the first one. So twice the frequency of the first one, you can see that that frequency differs as I'm moving down. So as I'm moving down, the frequency is increasing now. So now I have another wave, another sound wave that is going to produce a sound wave that is going to have 3 times that first frequency, the fundamental. So as I'm moving inside the same length, the number of circles, how the air molecules vibrate or how the strings vibrate, they also give the different frequencies. So as I'm moving downwards, the frequency is increasing as I'm moving. So now the first frequency there is what is called the fundamental frequency. And in the music production, it's actually what is called the base of the music. It is the first step of the music. When you get the base of the music, that is the fundamental mode. Now you look for instruments that have different frequencies that you can add to that fundamental mode. And those frequencies will be periodic, because you are making music. In that case, it must be periodic. So why is this man drop within, let's say, 1 second? This other guy makes 2 drop in the same second. Why is this other one makes 3 drop, as this is making 2 drop and this is making 1 drop in the same second? That you can see that you have a multiple of these fundamentals following. So the multiple of a number is the number derived when that particular number is multiplied by an integer. 1, 2 is an integer. If I have 1 times FO is FO, 2 times FO is 2FO, 3 times FO, and so on. So there is a fundamental multiple. There is a multiple of this fundamental here as I proceed downwards. So as the fundamental is the base, and the multiples of that fundamental keeps following that fundamental, then they will now constitute the quality. It is actually the number of the harmonics that are following the fundamental that constitute the quality of the sound. If more harmonics follows the fundamental, then you have a perfect mixture and you have a music that is of good quality or timbre. So the effect of the harmonics, that is the number of harmonics that follows that fundamental, is what constitutes the timbre, or also the quality of the sound wave. So the quality of sound wave is dependent upon the harmonic content, meaning the strength and the number of the harmonics that will follow the fundamentals give us the quality of the sound wave. So remember that is the property of the sound wave. We have intensity is loudness, frequency is pitch, and the harmonic content is that. So now harmonic content is quality or timbre. Remember that. Now we have the intensity. I just told you that the intensity of sound is the energy transferred, is the rate at which the energy is transported per unit area across that area across a unit area. So the intensity diminishes as the distance move. Like I just told you there is the example about the siren of this ambulance. As the ambulance is moving away from you, the distance is increasing, so the intensity diminishes, meaning the intensity reduces. So but we have a particular threshold at which we can perceive sound, and there is the faintest audible sound which humans can hear. That faintest audible sound is what is called the threshold of hearing. So what is the threshold of hearing? It's the of human ear. The human ear can detect sound with intensity as low as 10 raised to the power negative 12 watts per meter square, and as high as 1 watt per meter square. You can imagine that. Now, perceived loudness, however, is not proportional to the intensity. Now, if the standard threshold of hearing is chosen to be 0 level or 0 decibel, it is taken as the standard intensity, and it is denoted by I subscript 0. I can just emphasize that on the board for you. Now remember what I've said. I say your threshold. Threshold is actually a particular point in which an effect is bound. So there is a particular threshold of hearing where the intensity of that sound, never mind you are inside the audible range, but there is a particular intensity which is affected by the lowest audible sound. So the lowest audible sound has an intensity of 10 raised to the power minus 12 watts per meter square. Now that threshold of hearing is the faintest audible sound intensity which we can hear. It is IO, like I told you. Let's see how we can compare it. We want to calculate the intensity of this sound wave. Now, if they calculate the relative intensity, but before I get to the relative intensity, I first of all want to talk about the loudness, the effect. I've just already explained that. The effect of the intensity of sound is the loudness. I've explained that already, and it is the subjective feeling. The loudness is a subjective feeling, you know, and we have the relative intensity. So I'll go back to that question later on, but let me talk about relative intensity. Now, when I compare the intensity of the sound in relation to the threshold of hearing, I'll develop another intensity which is called the relative intensity. So relative intensity, which is, I want to give it beta in this case, it's when I compare the intensity of the sound produced, that's I, and the threshold of hearing, then I'll develop another quantity called the relative intensity. And because of its massive nature, we want to express it in terms of logarithm. So we can express it in terms of multiples of log. Let's say, for instance, calculate the relative intensity of sound of that intensity. Now let's take an example from what I've already said. So I can just put that for you. So now from that question, now it says the relative intensity is what we want to calculate. The intensity is given there already as 1.5 times 10 raised to the power 8 here. So we'll have 8 over there. So watch out. Now we have the 2, so we can evaluate. We can have, therefore, this is 10 log of, this is 1.5 times 10 raised to the power. Remember, this is a positive power, and that's a division sign. So we'll have plus 12. We have that stuff. Remember how the plus came, that's a division, that's minus. Minus is plus. So it's plus that stuff. You have 30. So we have 20 there. So I have 10 log. In that case, it's 1.5 times 10 raised to the power. If you like, you have 20 over there. So remember what you're trying to calculate. You're trying to calculate the relative intensity of that sound. So the relative intensity of the sound wave is given by that. Now, if you check the relationship as I've given you, we said the relative intensity is expressed as beta is 10 log. Now we have, what we have here is 1.5 times 10 raised to the power, this is 20. Now in decibel, we want to manage that. So now we have this, so we can do the math. This is 10 log. If you can evaluate that log, you have 1.5 plus log of 10 raised to the power 20. You know that already. So now we have 10 into log of that is somewhere around 0.176 for a fact, and this log to the base 10 is 20 already. You should know that already. So now what I've done is that if I drop this 20 here, I'll have log to the base 10. 10 is 1. 1 times 20 is 20. Let me go back there. I have, remember I just substituted the values of log 1.25 into that, and then plus I evaluated that. I was able to get 20 when I added these two, I got 20.176. So if you multiply that, you have that. That's the relative intensity of the sound for that question. So remember what we have said so far: loudness, and the loudness is subjective feeling. I've said that already. Now pitch is the sharpness and shrillness of sound. I've said so, and it's felt by the ear, and the effect of frequency is the pitch. I've explained that already. Now harmonics, if the frequency of overtones are tones after the fundamental, so are integer multiples of the frequency, which the frequency of the fundamental tone, that's just what I explained over there, then these are called the harmonics. I've already explained that. And timbre or quality, I said, is the effect of the harmonics content. So look at some questions as I have given you. Calculate the relative intensity of the sound with intensity 1.5 times 10 expo 8, 10 times 10, 1.5 times 10 raised to the power 8. Now we have the formula here. We say it is expressed in terms of logarithm. So we have 10 log the intensity of the sound wave divided by the threshold of hearing. That is standard threshold intensity of the threshold of hearing. We know that already. Now we divided the two, and we are able to express this. Remember the division line. So I got 8 plus 8 minus 12. That gives you 8 plus 12, that is 20. So we express the logarithm, when you multiply, you add the logs. That's what we did over there. We multiplied there, so it's log multiplied, it's adding plus the log of that. So I'll be able to substitute the log of 1.5 is 0.176 plus log to the base 10 power 20 is 20. So I added the 20 to 0.176, and you have 20 plus 1.176. So I multiplied. If you were able to get the 201.76 decibel. So that is the relative intensity of the sound according to that question. So now we're going to stop here for this lesson, and we'll continue again under the same sound wave with the next lesson. So watch out for the next lesson.